Hi, I'm Allan Gabriel Lariosa, third year mechanical engineering student. Today we are going to solve a problem using the Mohr's circle. But before we begin, let's start by reminding ourselves about the normal and shear stresses and the plane stress transformation equations. Normal stress occurs when the external force acts perpendicular to the cross-sectional area of any object or a body. It induces stress in those objects or a body to regain its original shape. The stress so produced by the perpendicular action of force on a given area is called normal stress. The force acts parallel to the surface area of the object. The stress induced in the object is called shear stress. As you can observe in the above drawing, the force F is acting parallel to the surface area, developing shear stress in the object. The general state of plane stress at a point is represented by a combination of two normal stress components, the normal stress X and normal stress Y, and one shear stress component Txy, which act on four faces of the element. The second figure denotes the new transformed axis, value, and direction of the plane. Sign conventions are if normal stress X and normal stress Y point outward, it is positive, and if shear stress Xy is positive, if it is turning counterclockwise, and negative in the clockwise direction. These are the plane stress transformation equations that we can use to determine the new orientations and values of the normal stress in the X and Y planes respectively, and the new orientation and value of the shear stress. The transformation equations for plane stress can be represented in graphical form by a plot known as Mohr's circle. This graphical representation is extremely useful because it enables you to visualize the relationships between the normal and shear stresses acting on various inclined planes at a point in a stress body. Using Mohr's circle, you can also calculate principal stresses, maximum shear stresses, and stresses on incline, and it is named after the German civil engineer Otto Mohr. He also developed the graphical technique for drawing the circle in 1882. The graphical method is a simple and clear approach to an otherwise complicated analysis. We have problem 7.32 for the given state of stress. Determine using Mohr's circle for 7.8 the principal planes and principal stresses. For 7.12, the orientation of the planes of maximum in-plane shearing stress, the maximum in-plane shearing stress, and the corresponding normal stress. To begin, let's identify the values of our normal and shear stress. For the normal stress in the x-axis, since it is to the right or outward, it is positive 16 MPa. For the normal stress in the y-axis, since it is going down or inward, it is negative 48 MPa. For the shearing stress in the xy plane, since it is in clockwise direction, it is negative 60 MPa. Next is to set our coordinate plane with the positive normal stress going to the right and the positive shearing stress going down. We put the positive shear stresses on the x-plane and the negative shear stresses on the y-plane. Next, we plot the points using the values of our normal stresses and shearing stress. Point A is normal stress in x and Txy, or 16 and negative 60. And point B is normal stress in y and negative Txy, or negative 48, and negative 60, or just 60. After plotting the points, connect it to make a line segment. This would also be the diameter of the Mohr's circle we will create. Determine the x-coordinate of the central point by adding both x-coordinates of the other 2 points, 16 and negative 48, and divide the sum by 2. Same with the y-coordinate of the central point. Add both y-coordinates of the other 2 points, negative 60 and 60, and divide the sum of 2. For letter A, let us determine the principal planes. These are the planes on which normal stress attains its maximum and minimum value. So these planes are also called as major principal plane and minor principal plane. The shear stress on principal planes is 0. We now have our Mohr's circle derived from the 2 points. First thing we need to do is to create a perpendicular line from point 16, negative 60 to the x-axis. The length of that line is equal to the shearing stress Txy. Second is to determine the length of the created line segment from the center to that perpendicular line. The length is equal to the difference of the normal stresses divided by 2. Since we created a right triangle with this, we can use the trigonometric identity tangent to solve for the value of the angle theta p. Tangent is just opposite side over adjacent side of the angle theta p. The opposite side is Txy and the adjacent side is normal stress x minus normal stress y all over 2. Substituting the values, we get tangent to theta p equal to negative 1.875. And so we get the arctan negative 1.875, which is negative 61.93 degrees divided by 2 gives us negative 30.96 degrees. Principal planes are 90 degrees apart from each other, so we add 90 to negative 30.96, which give us 59.04 degrees. Our principal planes are negative 30.96 degrees and 59.04 degrees. For letter B, we are required to find the principal stresses. These are the values of the normal stresses possible in the material. These are the maximum normal stress and the minimum normal stress. Maximum normal stress is called major principal stress, while minimum normal stress is also called minor principal stress. Major and minor principal stresses can be denoted as normal stress 1 and normal stress 2 respectively. We can get these values through adding and subtracting the radius r of our circle to the value of the x-coordinate of our center point, which is negative 16. The radius r of a Mohr's circle is also the maximum in-plane shearing stress. The center point is the average normal stress. We can calculate the radius r of a Mohr's circle through Pythagorean theorem. The length of the two sides of the right triangle is the normal stress x minus normal stress y all over 2 and the shearing stress txy. R is equal to the square root of normal stress x minus normal stress y all over 2 squared plus the shearing stress txy squared. Substituting the values, we get 68. So we add and subtract 68 to negative 16. Negative 16 plus 68 is 52. And negative 16 minus 68 is negative 84. Our major principal stress is 52 MPa and our minor principal stress is negative 84 MPa. For letter C, let us find the orientation of the planes of maximum in-plane stress. We have another right triangle with two sides with the length negative txy and normal stress x minus normal stress y all over 2. We can get the value of the angle theta s by using the trigonometric identity tangent, which is again opposite side over adjacent side of the angle. The opposite side is the normal stress x minus normal stress y all over 2, and the adjacent side is negative txy. Substituting the values, we get tangent theta s equal to 0.5333, and so we get the arctan 0.533, which is 28.072 degrees. Divided by 2 gives us 14.04 degrees. Principal planes are 90 degrees apart from each other, so we add 90 to 14.04, which give us 104.04 degrees. Our principal planes are 14.04 degrees and 104.04 degrees. For letter D, the maximum in-plane shearing stress. We already know that the radius r is also the maximum in-plane shearing stress. So let us just use the formula to calculate r, which is equal to the square root of normal stress x minus normal stress y all over 2 squared plus the shearing stress txy squared. Substituting the values, we get the square root of 4,624, which is equal to 68. Our maximum in-plane shearing stress is 68 MPa. E for letter E, the corresponding normal stress or just the average normal stress. We add the normal stress x and normal stress y, which is equal to negative 16. The corresponding normal stress is negative 16 MPa. That is how we solve plane stress transformation using Mohr's circle. Again, this is Allan Gabriel Lariosa, Padayan Engineering.